so much. Let me start by sharing my screen. Yeah, I hope everybody can see this. So yeah, from expressivity, from approximation to expressivity. So let's relate to the last lecture where we discussed the error decomposition. So here, this is copied from the previous talk. What we discussed is that the error which we are interested in can be estimated by an approximation error, an optimization error, and a generalization error. And so this lecture is targeted to understand the approximation side, so mainly to estimate the approximation error of the deep learning procedure. And so let me remind you how this was defined. So the R was the risk, and this function was just the minimizer over the hypothesis set, and the hypothesis set are neural networks, certainly in our case. So the question is, what is the error if I now approximate using an element from my hypothesis class instead of having, let's say, all possible elements available? And for instance, in the case of regression with quadratic loss, I can look at it this way. So this, just from the definition of the risk, is nothing else than this integral. This we already discussed just a couple of minutes ago. And this is the L2 error squared. And this I can also estimate, for instance, by the L infinity error. So this is what I would like to now estimate and analyze. And again, I mean, let me remind you the hypothesis set which we are interested in. And so this was our notation for a neural network. The little a indicates always the neural network architecture, because we made this distinction between the architecture and the realization of a neural network. And so the architecture are, this vector n indicates how many neurons there are in each layer, and the rho is the activation function. And so the psi a is then the realization, and the theta indicates the parameter, the set of parameters, and the number of parameters was defined to be, or as a notion defined to be P of n. Okay, so that's the goal. So the key questions which one asks in this area is, for instance, I have a given architecture. What is the expressive power of that? If I can now, let's say, change and have flexible parameters. Also, what impact has the depth of a neural network? Because what turns out is that deep neural networks are particularly effective, and that's actually why we now see basically such a success of this method. Then what about the complexity of the approximating neural network? That's a very vague question right now, because we didn't define what complexity is, but we will in a moment. Certainly you would like to approximate with networks of low complexity, in particular also complexity concerning storage. And also, what are suitable function spaces to consider? So if we approximate something, certainly we need good model classes. And the first I would like to formally define is the complexity. As I said, I mean, one can define the complexity of deep neural networks in various ways. What we want to do here is we want to take a viewpoint from memory. So we would like to have memory efficient neural networks. And so the complexity now is defined in the following way: of a neural network with this architecture and with weight matrices and bias vectors. We define the complexity by C of psi A as the sum of the L0 norms of the weight matrices and the bias vectors. Now, these are not really norms, but let's call them norm for now. So what this 0 indicates is that here one counts the number of non-zero elements. Yeah, so we basically count how many entries I need to store. The others are all 0, and that's my measure of complexity. Okay, good. So now, I mean, since there is already a huge body concerning approximation theory and many tools are borrowed, and it is also good to see what people have done before and then ask questions like, can neural networks do the same, or can they maybe even do better? I would like to review with you some elements of approximation theory first. that will also serve the purpose that we introduce some notions which we will use later on during the other lectures. So what does function approximation do or aim for? Typically, I mean, one has a class of functions, whatever you want, some model class, wherever it comes from. Let's here stick also to the Hilbert space setting L2 of Rd. And let's assume you have your favorite orthonormal basis for approximating elements. So then, I mean, the goal is to measure how good this representation system is for approximating functions in this class. Yeah, so that's a very classical general question of approximation theory. And the way this theory goes about that typically is in the following manner. We have an element of our function class, let's call it f. And then I have a budget, let's say n. And I can choose n elements of my orthonormal basis, for instance, and build a linear combination from it, like you see here. And I want to do that so that I get the closest to my f with this budget n. So I'm only allowed to choose n terms here. That's then a best n term approximation. The best I can do with n terms concerning approximation. Yeah, so the name is program in that sense. I also make an error that way. That's the error of best n term approximation. Okay, so now, I mean, if I have, let's say, for instance, a basis or a complete system, I let n go to infinity, then the error will converge to 0, and people in that area ask at which rate does it converge. And this rate, so one can indicate it this way. So what I would like is that this behaves like O of n to the minus gamma. And the larger gamma, the better, because then with very few terms, I can already approximate my f with very high accuracy. So that's the approximation rate. So what this basically does is it sets into relation, on the one hand, the approximation accuracy, so this arrow, to the complexity of the approximating system in terms of sparsity, because what you aim for here is very few terms. You would like with a very small n to get already a very small error. So that's, in a nutshell, I mean, one main goal. Okay, so this I would now like to fill with a bit of life, and what we will introduce, as I said, I mean, we will use for this talk and also for subsequent talks. Some of those. A very classical model class for certain reasons are cartoon-like functions. So they look like this. You see here, they are smooth in most parts, only they have a very distinctive discontinuity curve. So this can be, for instance, viewed as a model, a crude model for imaging to some extent. It can also be used, for instance, solutions of transport equations also exhibit, in a certain sense, phenomena of that type. And in general, I mean, multivariate functions are typically governed by these, let's say, directional-based singularities. And so these are called cartoon-like functions. You see the definition here. It's from Degg-Donohoe in 2001. You have two functions, f0 and f1, which are both smooth, C2, compactly support on the unit square, and then you have this area B, which basically cuts one of those functions and creates this discontinuity. Okay, so that's a function class. And what we also showed is that this approximation rate, which we saw on the previous slides, let me go back. So this gamma here, this approximation rate, one can actually bound. The best one can achieve is 1 for gamma, so n to the minus 1 is the rate. So there are certain conditions for this result, which mainly exclude artificial cases. Okay, so no matter how good I can choose my representation system, I will not get a rate which is better than this, but maybe worse. And now, I mean, one of the maybe most famous systems is the system of wavelets. A wavelet system looks like this. You have here one function which you move around, and where you also have a means to zoom into the signal. So this J is like a scaling factor. You can squeeze the function, you can stretch. And then it also has a different content, which is mainly responsible for the low frequency. So if you take a frequency viewpoint of these systems, what you observe is that if this is, let's say, the frequency axis, so the domain of the Fourier transform, then the essential support of the Fourier transform of this is in this low frequency part around 0, and the support of the Fourier transform of these functions, depending on J, is in these areas or these areas, and so on. So that way you tile the Fourier domain. And so you can also map it to R2, or map, I should say map. I mean, you can extend it to R2 by tensor products. You see it looks basically similar. Again, you have a function which you move around and which you scale. And here you see how these wavelets tile the Fourier or frequency domain depending on their J's and the different functions. And so one can show that wavelets are really good, for instance, in approximating point singularities, but not that good on cartoon-like functions. But I mean, the main purpose of wavelets was also compression. Wavelets are the basis for the JPEG 2000 compression standard. And so what a wavelet transform does, so if you have here your F and you compute now inner product of F with your wavelets, you get something like this. So you see a wavelet is able to extract the singularities in a meaningful manner at different scales. And that way, I mean, I don't want to go too much into the details there, just give you a flavor of it. That way you get very high compression rates without much distortion. So what you basically do is you just store the components which are enlightened here, so which are white, and the others which are black, you just throw away. And so that way you get high compression rates, and that leads you to these very effective compression standards. But now for our purpose, these wavelets, which we saw on the previous slide, so here's one part of it, are not that good for these cartoon-like functions. Yeah? So that's the main point here. Why? Because they don't scale that way in both directions. They just scale in the same way. Yeah, and so these wavelets, yeah, so the scale is always 2 to J, and basically if you now have these distinctive discontinuities and you would like to really efficiently approximate it, you don't do a too good job with wavelets because they are like a little square. Yeah, and you only get a rate of n to the -1/2, which is very far from n to the -1. What would be much better would be if you would have anisotropic shaped elements. And so there was a lot of activity to create those, and as Carola already alluded to, I mean, we then introduced shearlets, which we think is a quite effective system, and let me briefly introduce these now, and we will use them, for instance, also later on when we come to inverse problems. So in contrast to wavelets, shearlets scale differently in both directions. So that produces elements like you see here, which have a directional component. They have basically a length of 2 to -J½ and the width of 2 to -J. So as J goes to infinity, they become like a little needle. Now, since they are anisotropic, so direction based, you also need to change the direction to basically be able to approximate any curve. The changing of direction is done here by a shearing matrix, not rotation, because rotation would destroy the digital grid, so it would not give a faithful implementation. But with shearing, that's possible, and so then one can define formally these discrete shearlet systems. You see here again the translation on the plane, this M, and then you see here the shearing and the parabolic scaling operator. And so you see here how the frequency domain is tiled in a very, very fine manner. You see it's, if you compare, let me go back to the wavelets, you see also there a striking difference. Wavelets tile the Fourier domain in this way, but shearlets are much more precise concerning the different directions, so resolve them in a much better manner. Okay, and I mean, last but not least, these systems under certain conditions, even in the regime where these elements are compactly supported, they give us this magical n to the -1, this optimal approximation rate up to a log factor. Yeah, so if you view a log factor as negligible, then you can say these systems give the optimal approximation rate of cartoon-like functions. Yeah, so that's very nice. So we generated systems which meet this benchmark result. And I mean, if you're interested in that and would like to try things out, I mean, you can use this also for certain imaging tasks. I mean, that we will discuss a different lecture, but you have a lot of demos here on the webpage shillab.org, and we have it in different languages, so you can just go there and play a bit around and try this out. But the main point here was to fill this with life. This is the slide we already saw. So this could be cartoon-like functions. This could be a shaded system. And then this gamma equal to 1 was the optimal rate. And we showed that up to a log factor, shaded actually meet that. Okay, so this gave a bit of insight into classical approximation theory. And we will now come to deep neural networks. And you will see then, I mean, throughout the talk that we will use certain elements also from approximation theory for that. So there's a very classical result concerning neural network approximation, which is the universal approximation theory. But let us start very slowly and let's look at this remark. So we have here our activation function. Let's assume the activation function is a polynomial. And so then we have here the weight matrices and the biases. Now, if this is anyhow, I mean, this is linear. And then I have here a polynomial. So if this is a polynomial of a certain degree, then my realization, if this is my tiny neural network, and sorry, if now I take L layers of that, I will get a polynomial of degree L times Q. I cannot go beyond that. Yeah, so in that sense, I mean, if I now choose such an architecture, let's say with 2 layers, I will never be able to approximate, for instance, the continuous functions, because I always end up with a polynomial of a certain degree and I cannot go beyond that. The essence of that is choosing the activation function to be a polynomial is not such a great idea. And so now the next result, which is the universal approximation theory, also does not do that. So it chooses the activation function to be continuous and not a polynomial. Okay. So what does this result now say? Well, I mean, I have a continuous function defined on a compact domain. And I have my activation function continuous, not a polynomial. So then I choose an accuracy epsilon. And then I will find an n. So that with a shallow neural network like this, and you see how these look like, they just have one hidden layer. So shallow neural networks of that type, I can approximate this f with that accuracy. Yeah. So in the infinity. So that was the first highlight in expressivity, which says, so here it's let's say in words, every continuous function on a compact set can be arbitrarily well approximated with a neural network with one single hidden layer. So that's very nice. So let's look at the idea of the proof. So what one would like to prove, this is even a bit more than what is stated in the result, is that the span of these neural networks is dense in the continuous functions, if and only if rho is not a polynomial. Yeah, so one of those directions we already saw. So now that was already marked. So now we would like to go from 2 to 1. And just for d equal to 1 and a smooth activation. Now, if rho is not a polynomial, what I know is I find a point where all the derivatives do not vanish. So this I cannot use. And I use it in the following manner. So first of all, I would like to show that, so I would like to now show that the span is dense. So first I show that continuous functions can be arbitrarily well approximated. This I can do in the following manner. I look at this element of these networks, and I let h go to 0. Since rho is continuous, it converges to rho of minus x0. This is not equal to 0, so I can multiply it with any value, and also this I can multiply with any value. And so that means I can create a sequence in here which converge to a constant function, and I can choose any constant function there because I can just multiply with any. So constant functions I can arbitrarily well approximate, and I can do the same for linear functions. So here I need to choose a bit more complicated expression, but still these are elements of the span. Now I let h go to 0, and I also let lambda go to 0. So that brings me to this element, x times the derivative of rho and minus x0. This is again not equal to 0. So again, I can multiply it with any element. And that means I can approximate any linear function, and so on. And so you see this can go on and on and on. And basically that way one can show that any polynomial can be well approximated. Then we use Stone-Weierstrass and show this for d equal to 1. Then we can extend it to d arbitrary, and then we also need to get rid of smoothness. But that is the idea of it. And so this is the result which we then prove. So that's very nice. I mean, in this situation, this leads us to relating back to the beginning of the talk that the approximation error converges to 0 when the complexity of the neural network increases, because here, I mean, the n will increase depending on x. Okay, so that's the very first result showing that we can bound the approximation error. But we would like to set more into relation the approximation accuracy and the complexity of the approximating neural network, and maybe even get an optimality result. And so in this regime, I would like to show you one result. Typically, results, I should say, are based on the so-called VC dimension. And the VC dimension we will meet it later on in lecture 4, but here I would not like to use this classical approach, but a bit more modern approach, and which also answers other questions. So first of all, I'm interested in approximating functions by neural networks with low complexity, with very few non-zero weights. And I would like to do that in an optimal manner. And so what I need is a lower bound for the complexity, and then constructing neural networks which meet that bound. But what I'm also interested in is I would like to know if neural networks are as good as what people have done before, as previous approximation schemes, like wavelets and shearlets, like we saw. And so with this approach, which I would like to show you, we can answer all those questions. We can create memory optimal neural networks, and along the way, we can show that neural networks perform as good, at least as good as all those previous ones. So for that, we first need the lower bound. And for the lower bound, we need a measure for the complexity of a function class. So you might have heard of Kolmogorov entropy. We will use here something similar. Since we use results from information theory, we will use the optimal exponent. But basically, I mean, if you know Kolmogorov entropy, you can substitute that also. So here, this optimal exponent, which is a measure for the complexity function class, describes the dependence of the code length for encoding a function class on the required approximation quality. You will see that in detail in a moment. But what I would like to show or state here is that this is also interesting in a different respect. Remember, we had here this mysterious gamma, this n to the minus gamma. And this gamma one can actually express with this optimal exponent. Yeah, so this is nothing else than n to the minus 1 over gamma star of c. Yeah, so this is directly related to the optimal approximation. Okay, so what is this optimal exponent? I said it comes from information theory. Now, information theory deals with coding and encoding, and one can define it in that way. So encoder are just maps from, let's say, L2, from functions to a code, to a bit string, and a decoder maps it back. So that's nothing mysterious. What one would like to have is that if we first encode and then decode, that then the result does not deviate much from F. Yeah, I mean, that's something natural, like also compression. And so we say that such a pair, an encoder-decoder pair, achieves distortion epsilon if this is true. The error, the worst case error, is still less or equal than epsilon. Okay, so this is, just take a look here. So we now look at encoder-decoder pairs which achieve this distortion, so which are benign in that manner. And certainly the longer these codes, the easier things. I'm now interested in the minimal length of the code so that this is still true. So this is the minimal code length, and then, so epsilon was everywhere fixed here. Now I let the epsilon go to 0. And then I'm interested in the rate of this minimal code length. Now, because then if my epsilon goes to 0, the minimal code length has to go to infinity, and I'm interested in this way. So that's the optimal exponent. Yeah, I mean, we don't need to go into the details. Just think of it as an appropriate measure for the complexity of a function. And then, I mean, one can show the following result, which shows a lower bound for learning type algorithms concerning the complexity of the resulting neural networks. And so this states the following: I have an abstract learning procedure which takes an accuracy and an element of my function class, and it computes a neural network, and this in my hypothesis class, which approximates these Fs with that accuracy. So that's basically a deterministic manner way of seeing what a learning algorithm does. And so then, I mean, what I can show this lower bound now is an asymptotic lower bound. I can show that the complexity of these resulting neural networks, so there's no C, so that the complexity is bounded by C times epsilon to minus gamma. So that shows basically that the complexity is always in an asymptotic way lower bounded by this. So it gives you a lower bound for all of these gammas, gamma less than gamma star of C. And gamma star again was this optimal complexity. So it shows me a lower bound for the complexities coming out of such an abstract learning procedure. So the neural networks need to be sufficiently complex. And I mean, the proof is basically relying on looking at the complexity and then looking at the complexity of the neural network, encoding everything in bit lengths, and then basically doing bit counting, and then this gives this result. Okay, so the big question is now what happens in the limit case. I mean, the hope is that maybe there we get something like equality here, and then these would be memory optimal neural networks. So then, I mean, when we come to construct. Okay, so how do we get there? Now we use everything what we learned about approximation theory, because now we transfer approximation theory to the neural network setting. So what we do is, first of all, we have, let's say I have my function class I would like to approximate, and I have a representation system. So now, for each of these systems, remember these realizations of neural networks are functions. So elements of my representation system, like Scheele's, for instance, I can build little neural networks which approximately represent and mimic that. So for each of my functions from my favorite representation system, I build a neural network which has a constant number of edges. So for instance, neural networks of these types, which are functions from R2 to R. And so I mimic each of the elements of my system by a neural network. Then I can build an n-term approximation in this manner. Yeah, so that's an n-term approximation encoded in neural networks. Here I have all my representation systems. And then you see I sum that up. And the weights Ci are on these connections. Yeah, so what this does is it basically transfers this idea of n-term approximation now to neural networks. So now I have a neural network, and how many edges does the neural network have? Well, I mean, since this has O of 1 edges, and I have M connections here from this M, this has O of M edges. Okay, so now we can construct a neural network which mimics an m-term approximation. That's already great. And this is already, so this is just copied from the previous slide. Now I need to bring it into relation to my approximation class. To my class, which I would like to approximate. And remember, so if we have our favorite class, and if I have an F here, then the best I can do in the approximation was this minus gamma, and I said we can replace this by this optimal exponent, because this gamma, this optimal approximation rate, is nothing else than 1 over gamma stars. So this is basically, again, what comes from approximation theory. And now if you put everything together, what one can basically show is that every f can be approximated up to an error of epsilon by a neural network with that many edges. So how can one come to that? We already saw that this I can mimic by a neural network with m edges. So now I have here f minus my realization of my neural network. And I would like this to be less or equal than epsilon. So I set this equal to epsilon, and then I solve for m. And then I get m is equal to O of epsilon to minus gamma star of c. And so I have a network which approximates f up to epsilon with that many edges. And so this is nice. Why? Because you see, this is copied from our previous result, which says there's no constant, so that, sorry, this needs to be a C, so that the complexity of these learned neural networks behaves in this way. But now we found a neural network where the complexity is of this type. So this shows that via this construction, we can create neural networks which meet actually this lower bound. And now, I mean, not going too much into the details, but let me say what we now achieved was, if we have a favorite class of functions, like cartoon-like functions, and we know a representation system which gives these optimal approximation rates, then, I mean, if we then can mimic every element of this representation system by neural networks with a controlled number of edges, I'm done. And then I can meet this lower bound with using neural networks which come out of this n-term approximation procedure, which are just created by transferring classical approximation theory in the neural network world. The only thing which is missing is whether we can actually build neural networks which realize these elements, like, for instance, shear length with a controlled number of edges. Now, this can be done. We will see that also a bit later again. And so we take here ReLUs. And what one can show, and this dates actually already back to Jan LeCun in 1987, where he wrote his PhD thesis, and already there he built certain functions with neural networks. And with the ReLUs, it's very nice. So for instance, there you can build little functions which look like this. So like a little bump function. This you can do. You see, this is a 2-layer neural network. You have here these affine linear functions, and then you have activation function here. You can then bring it into the 2D world, like where shillets live in. So functions defined on R2 by building combinations of this type. You see here you have T here involved applied to the first component and the second component, and again the ReLU. This leads to BAM functions like of this type. And that way you can create useful elements, like for instance, V3 researchers created wavelets that way in a certain manner, which I don't want to delve too much into. You need to do some tricks there, so basically move it around to create what's called vanishing moments. But in any case, using a 3-layer network, one can create, for instance, wavelets, for which also then the theoretical results hold. For our proof, we needed a bit more. We needed differentiable functions, which was really is not possible. So we used the out version of ReLU, but basically, I mean, you can think of this as ReLU. So this is a program where you can also, for instance, create shearlets, which you can then also use rigorously for the results and for the proofs. So here, again, I mean, to summarize, you can use 3-layer neural networks to mimic shearlets, which you can then use, as we saw before, as a component for your proof. And so this leads to a result of the type with a certain type of activation functions. So this admissible relates to, for instance, this smoothed out version of ReLUs. We have an accuracy. Then for any Kutyniok function and for any n, I can construct neural networks with 4 layers and with this complexity. So that's the complexity I aim for, so that the error which I make behaves like this. And you see here again this magical -1 into the -1, but still this epsilon. And maybe it's not that surprising that you cannot get exactly the rate, because also with shearlets themselves, as I said, I mean, you can only get that up to a log factor. So in that sense, that is the optimal rate up to this epsilon. So the first bound is sharp. And so basically what one can show this way, this is now for shearlets, but one can also use other types of other types of classes of functions and other representation system. So this is a very flexible procedure to transfer results from approximation theory to the network world. So in general, one can say that function classes which are optimally representable by shearlets, for instance, like these Kutyniok functions, are also optimally approximated by memory efficient neural networks, so where the complexity is of that order which we aim for, even with a nice architecture. Now, because these neural networks have a nice parallel architecture, they are not deep. Okay, so now the question is certainly, I mean, that is a theoretical result, and we are also interested in mathematics of deep learning, but still one would like to ask, what about real life when we train these neural networks? Yeah, so one can ask the question, I take neural networks now of that type, and I just train them. Yeah, so now the way I train it is I take a function and I take samples of this function, and I train the neural network on those samples. And the question now is the following. Remember, when we build these neural networks, so these were n-term approximations, and in these compartments, I used, for instance, wavelets, I used, for instance, shearlets, and so on. So these are functions here from R2 to R. And so one can now ask, if I train this neural network fully, what functions does it learn in these compartments? And what one can detect is something quite interesting. So we trained it to stochastic gradient descent, and the result was something like this. So this is the first function we trained it on. It's a classification function. So we took samples here. Yeah, so this is the function from R2 to R. Yeah, so we took samples, we trained the neural network, and not that unexpectedly, the number of edges or the complexity relates to the approximation error in a manner which is close to the theoretical result. But what was very interesting is that in these compartments, the neural network actually learned something like those functions. And if you look at it from a theoretical viewpoint, these functions are close to so-called Dirichlet's, which are actually functions which you would use also to approximate the function of this type. Yeah, so here the network could sense, in a certain sense, which are good representation systems for approximating this function, just by using this particular architecture. And so this also shows how with the selection of an architecture, you can actually also tune a neural. And so this is another example where we have a curvilinear singularity, and again we take sample points here, train our neural network. Again, the error is something what one would expect, this error curve, but then interesting, these compartments, one learns, or the neural network learns something which looks a little bit also like shears. Yeah, so in that sense, I mean, the neural network, one can say the neural network is actually able to maybe mimic applied harmonic analysis in that sense. So this showed that what people did before, like wavelets and shearlets and all these approximation schemes, one can also do at least as good with neural networks. And one can also along the way create neural networks that way, which gives this optimal approximation rates also with low complexity. But this does certainly not explain why deep neural networks are that effective, because what we just talked about are actually reasonably shallow neural networks. So one can certainly specifically in this area of expressivity also ask the question of depth. What role has depth? And so for that, we will again consider the ReLU activation function. And the first what one observes is that if we have, for instance, again, a two-layer neural network, shallow neural network of this type, that this, if I have a ReLU, is always a continuous piecewise affine linear function. And so this piecewise affine linearity we will see can be used in different ways. Okay, so first of all, I mean, yeah, so the role of depth is what we aim for. Now, let's first take a look again at a very tiny example, which we'll then extend and use to show basically what effect the depth has. So an easy example is the head function, which is also used, for instance, for finite elements in PDEs and various other instances. The head function is a very easy function. You see it here. You can realize it with a neural network with two layers and two neurons. So that's my neural network. Basically, it's like this. And you can easily check that this equality holds. So if it's in between here, then this part is equal to 0. So this gives me 2x. And if this is in between here, you can subtract this and you get this. Okay, so now I have this one head function, and I'm interested in the role of depth. So what I can do is I can now concatenate this many times. So that's a kind of boring neural network, but still it's a neural network which with a certain depth. And that way one can create the so-called sawtooth function with actually two n spikes. Yeah, and so that's the key observation here, that if we have, let's say, an n-fold concatenation, convolution is maybe not the right way, concatenation of these h's. So then I can create a sawtooth function with two n spikes. So as it says in particular, hn admits 2 to n affine linear pieces with only 2n many neurons. So that means that that's an indication how effective this depth is. So deep ReLU neural networks are exponentially more efficient in generating affine linear pieces. So that goes up exponentially. That makes it so effective because we have this compositorial structure in the neural network. Now, with this observation, one can also use to create various functions and then also see what the role of depth is again. And so this follows ideas by Jarodsky, where he wanted to approximate the quadratic function with neural networks. So for that, let's now this IN be an interpolation of this function at that many points. So this function G you see here, it's strange colors, it's brown color or deep purple color. And this I1, I would now like to be interpolation with just 3 equidistant points. And so what you see here, maybe first take a look here. So this I1 is just this function. It interpolates G at 3 points, namely at this point, and at this point. Then if I take the difference, G minus I1, I get this red curve. And again, I can interpolate that now at these 5 points. And again, I take the difference, I again get these bumps, and so on and so on. Yeah, and so this you see here. Yeah, so these INs are always interpolation of this function at that many equidistant points. So at 3, 5, and so on. I can write IN as this sum, so that's telescope sum, so you easily see that all of these components vanish, and only IN then remains, and I0. But the nice thing is that you can actually write it in terms of these HKs from the previous slide. Yeah, and so here now you have a relation, the HKs, these are specific neural networks, and so that way you can actually, coming now back from this expression, you can express this quadratic function now in terms of neural networks. So that's basically the idea there, and which you also use then to create explicit functions by neural networks with a certain depth. So that leads now to efficient approximations by real neural networks of this quadratic function. That way you can also extend it to multiplications, to local Taylor polynomials, to smooth functions, regular functions, and so on. So this is the whole program on how to approximate in a very, let's say, conscious manner and structured manner functions. But what you see here is that way you get also an indication of depth of the number of parameters. So this is, for instance, one result of that type. So that where, I mean, this is about Sobolev spaces where one can show that for every accuracy one can find a neural network architecture where the number of parameters here is actually bounded, so that for every element of my Sobolev space the approximation error is bounded by epsilon. So that creates a whole program. I mean, still this doesn't show that you cannot get away with lower, with fellow neural networks, but it still gives you an indication on how effective depth actually is. A better, let's say, relation between depth and approximation accuracy and width is, for instance, this result by Jarodsky. So here he explicitly showed that there is a trade-off between the depth and the width in approximation and the approximation. Yeah, so that's a very interesting result. And what it says, you see, is the following. So I have a number of layers. I have my G, which is the C2 function. And not affine linear. So then I find a constant so that for every accuracy, I can find a Rayleigh network architecture with L layers. And so now comes the interesting part, you see, and the number n is bounded, so that bounds the width of the neural network, so that the approximation error is lower bounded. So that you have actually a better approximation error. You would need to go beyond either the number of layers or beyond the width. So that in a way creates a very nice lower bound for approximation in relation to the width of the neural network and the number of layers. And I mean, so this area is basically exploring. There are numerous results on expressivity. Let me also maybe just briefly mention the proof here, or the idea of the proof. So this relates again to the fact that real neural networks are piecewise affine linear, and then one counts basically the number of pieces if one has architectures of that type. In that way, one can then show that if you have certain conditions here on the number of layers and the width, you don't have enough expressivity, and so therefore you get this lower bound. So that is what's in the background. So as I said, I mean, there are numerous results, different function classes, and so on and so on. I mean, it's a huge area. But I would like to, in the last few minutes, also mention a different notion of expressivity, which I find interesting, which does not really directly come from this approximation theoretic viewpoint. And so this is related to, one aims now to relate structural properties of the neural network, not with the approximation accuracy, but with, I say here, the richness of the set of possibly expressed. So the question is, what do you mean by the richness of that? I already said, if you have real neural networks, the realization of those, you can identify the affine linear regions it's split into, and you can certainly count them. And so there are various works, particular also by Guido Montufar, who are they count the growth of this number depending on the depth. So what are these affine linear regions? Well, I mean, these are those regions in the input domain where I exclude sets of non-differentiability, and then the affine linear regions are the connected components of those. So, so if this is, let's say, the picture in here, in all those areas, the function, the realization of the network is affine linear. So then I would have here 1, 2, 3, 4, 5, 6, 7 different areas, affine linear areas. And again, I mean, there are also various results in this respect, for instance, also from Sarah van der Geer, where basically the message is that deep real neural networks can exhibit significantly more regions than their shallow counterparts. In fact, exponentially many, and so the effect, again, I mean, these results are all done by counting arguments, where you look at neural networks, and you see here, if you have this very tiny neural network, which is just basically one layer, then because of the structure of the ReLU, that's the max of 0 and x, you get 2 regions which are separated by this hyperplane. And then you can certainly count. Now, if you increase the number of neurons, and if you can decrease the number of the depth of the neural network. So if you have, again, a shallow neural network, you get a separation, you get these n hyperplanes which separate your space. So you get a bound for that. And then if you deepen the neural network, you get foldings of spaces. So then you can count how many elements you have. And so basically, again, I mean, you get exponential efficiency of deep neural networks for generating affine linear regions. So in that sense, again, I mean, the depth leads to an exponential increase in expressivity in this sense. So this is counting the affine linear regions, which is also certainly one way. And you saw that this also relates, and these techniques were also used for proving results from these approximation theoretic type. But you can go also one step further in a bit different direction. And the idea here is, as I said, more the richness of the functions which are created. And so what the idea here was to take a non-constant curve in the input space and move it through the neural network. So something like this. So you have this input curve, and then you move it through the layers. And it becomes more rich in a certain sense, I mean, meaning also the length increases. So you can ask also to which extent the lengths of these resulting curves depend on the number of layers. And so this was used by those colleagues to have a different notion of expressivity of neural networks. Yeah, so this is, as I said, we have a real neural network, we have a non-constant continuous function input space, and we are interested in the length of the trajectory of the else in the else layer as we push that through the neural network. And so the length of the trajectory is then a measure for the expressivity of the neural network at that point, at that layer. And so then I'm going to analyze the length, look at the expected value of that, and so you can, for instance, follow an argumentation of this type. If you start with parameters of your realization, which follow a certain distribution, then one can argue that the expected value of the length of, if you push now your curve through, is positive. And if you use a different distribution, then because of the homogeneity of ReLU, you can pull the sigma out. So following an argumentation of that type, what would then be shown by these colleagues is that the expected value is sigma to L times constant C. And so this again relates to this exponentiality, that the expected trajectory length depends exponentially on the depth. So this is in some sense another instance on how you can view and analyze the effect of depth on expressivity, however you define expressivity in this range. Okay, so let me conclude. So this talk was about, this lecture about the approximation error, which, as we saw, is one of the three components of the errors which we need to estimate from statistical learning theory. We saw that deep neural networks have a certain universality property. We saw this famous universal approximation theorem. And then we also saw that neural networks are as good as many methods which people have used for approximations before, like wavelets, shearlets, and so on. Concerning the depths, also here we find in this theory indications why depth is interesting and useful, and why deep neural networks perform that much better than shallow neural networks. So here that deep neural networks could be proven to be exponentially more efficient, for instance, in generating these affine linear pieces, but also in this, let's say, alternative viewpoint of expressivity considering the length of the trajectory. And with this, I'd like to thank you very much for your attention.